Machines understand the world through mathematical representations. In order to train a machine learning model, we need to describe everything in terms of numbers. Images, words, and sounds are too abstract for a computer. But a series of numbers is a representation that we can all agree on, whether we are a computer or a human. In recent shows, we have explored how to train machine learning models to understand images and video. Today, we explore words. You might be thinking, isn't a word easy to understand? Can't you just take a dictionary definition? A dictionary definition does not actually capture the richness of a word. Dictionaries do not give you a way to measure the similarity between one word and all other words in a given language. Word2Vec is a system for defining words in terms of the words that appear close to that word. For example, the sentence, Howard is sitting in a Starbucks cafe drinking a cup of coffee. That sentence gives an obvious indication that the words cafe and cup and coffee are all related. With enough sentences like that, we can start to understand the entire language in terms of words relative to each other. Adrian Colyer is a venture capitalist with Excel, and he blogs about technical topics such as Word2Vec. He's also written about databases and many other technical topics. You should check out his blog if you're curious. The link is in the show notes. We talked about Word2Vec specifically and the deep learning space more generally. We also explored how the rapidly improving tools around deep learning are changing the venture investment landscape. If you like this episode, we've done many other shows about machine learning with guests like Matt Zeiler, the co-founder of Clarify, and Francois Chollet, the creator of Keras. You can check our back catalog by downloading the Software Engineering Daily app for iOS, where you can listen to all of our old episodes and you can discover new topics that might interest you. You can upvote the episodes you like. You can get recommendations based on your listening history. And if you are interested in contributing to the Software Engineering Daily app ecosystem, we've also got an Android app that we're working on. We've got a web front end, and we've got a back end recommendation system to improve the recommendations. There are only 600 episodes in our corpus, but it's a wide set of data since we've got audio and everything. So it's kind of an interesting set of problems. If you're interested in contributing, you can go to github.com/softwareengineeringdaily. And with that, I hope you like this episode. To build the kinds of things developers want to build today, they need better tools, super tools, like a database that'll grow as your business grows and is easy to manage. That's why Amazon Web Services built Amazon Aurora, a relational database engine that's compatible with MySQL or PostgreSQL, and provides up to 5 times the performance of standard MySQL on the same hardware. Amazon Aurora from AWS can scale up to millions of transactions per minute, automatically grow your storage up to 64 terabytes if need be, and replicate 6 copies of your data to 3 different availability zones. Amazon Aurora tolerates failures and even automatically fixes them and continually backs up your data to Amazon S3. And Amazon RDS fully manages it all, so you don't have to. If you're already using Amazon RDS for MySQL, you can migrate to Amazon Aurora with just a few clicks. So what you're getting here is up to 5 times better performance than MySQL with the security, availability, and reliability of a commercial database, all at 1/10 of the cost. No upfront charges, no commitments, and you only pay for what you use. Check out aurora.aws and start imagining what you can build with Amazon Aurora from AWS. That's aurora.aws, aurora.aws. Adrian Colyer is a venture partner at Excel. Adrian, welcome to Software Engineering Daily.
Thank you. It's a pleasure to be here.
We got connected because I emailed you about a blog post that you wrote. I read your blog on a semi-regular basis, you do a good job of condensing technical works, whether they are papers or talks or just computer science concepts, and synthesizing them into well-written, digestible blog posts. And I think this has synergies with your work as a venture investor, because oftentimes you're making technical investments. So I'd love to start off by talking a bit about blogging and how that fits into your workflow. How does blogging fit into your day-to-day workflow as an investor? How does it provide you value?
Okay, great question. Yeah, I mean, I guess it definitely does help with what I do, in my role at Excel, but it's also a passion beyond that. My career history was technical in a variety of CTO roles, and so that's really where the love of computer science comes from. And so I guess there's two sides to how it fits in. One is, where do I find the time, which is a very frequent question, because it's reading and writing up a paper every day. And then, related to that, sort of, how does it pay off? And maybe you were leaning more towards the second one. Let me take that one first. Sort of, it pays off in very surprising ways. And I can never really predict, which things I've read or I've looked at or I've studied are going to turn out to be useful. But it is frequently the case that I'll be in a meeting with an entrepreneur who's doing something exciting, and it'll turn out that, just last week I read a paper that was related to this, and we'll be off and we build a quick rapport. And so it's useful in that way. It's also very useful in getting a good feel for where things are going, which of course is invaluable if you're going to be investing, and also just for looking at lots and lots and lots and lots of problem and solution pairs, which you tend to find in all of these research papers, which sort of trains you to quickly, get to the bottom of an idea, understand the key trade-offs, and sort of evaluate its merits rapidly.
And, one thing I've noticed from surveying a lot of ideas, I survey a lot of ideas just from doing the podcast, and it's interesting because, one phenomenon I had recently was I interviewed somebody from Facebook and somebody at Squarespace, both of whom were building these image similarity search engines, and they built them, I think, almost at the same time, and totally disparately. But it's interesting because it almost seems like there is something about I guess this has been happening, since calculus was discovered simultaneously by two different people. But there is something in the air where once the tools get to a certain place, a bunch of people at the same time, or at least two people at the same time, will realize that something is possible that was not possible before. And I suppose if one person is an investor and the other is an entrepreneur who's building that, that can be some pretty good fit right there.
Absolutely, yeah, and I think it really does happen. That sort of ideas are in the air, and your similarity search is a great example. Actually, it touches on a topic we'll be talking about today. So if you think about going back to the idea that, hey, there are these word vector things and they can somehow encapsulate the meaning of a word, and then this was extended to paragraphs and sentences and documents and then to images, etc. And well, we can compare these vectors. And so that the groundwork is done to say, well, if we can do all of that, then we can do things like similarity search in interesting ways.
Mm-hmm. Investors often write investment memos to their partners or to themselves. Does the process of blogging about technical topics, does that at all relate to your ability to write investment memos, or do you even do those kinds of things?
So absolutely, we do investment memos. That's a key part of our process, so we always do that. So it's interesting. I mean, I wouldn't say that the kind of material I write in my blogging is quite different from an investment memo. In a way, I mean, in both cases, you're making the case for something, but I do write very frequently, through the blog, and I do communicate a lot with external people, and I think that helps. The last investment memo I wrote, one of the partners came back to me and said, well, wow, actually, you're really good at explaining complex ideas simply, and I think that's just practice. I do it nearly every day.
Mm-hmm. Yeah. Okay, well, let's get into the discussion of word vectors. What is a word vector?
Yeah, great question. And so word vectors are these really curious things that sort of certainly capture my imagination, and I think that of many other people. And it's the idea that somehow a string of numbers can come to represent the meaning of a word in the sort of the highest level. And so sort of if you go back in time when we were doing sort of processing with words, etc., it used to be that you'd use what's called a one-hot encoding, or sort of one of n encoding, in which you can imagine sort of say you have a world which has got 100 words for simplicity, and you'd have sort of a binary string in which all the entries are 0 apart from the one that represents your particular word, and so that you turn on the bit for the word sausage, for example, and there you have your vector that encodes the word sausage. But that's not very interesting because it's just one bit. And what began with the papers from Mikolov et al. Was this idea that actually what we could do instead is we could have a very high dimensional vector, so sort of an array with many, many numbers in it, hundreds of dimensions, and that could somehow come to represent the meaning of a word. And how it represents the meaning of the word is that we look for the context in which that word is used in a variety of ways, which we can get into. And we use machine learning to build up the weights in this vector such that actually it becomes a good predictor of other words that are often found in its context. And when you do that, a lot of surprising properties fall out that I'm sure we'll get into. But this is the basic idea that sort of, instead of just having a one-hot encoding, you have a whole string of numbers that come to represent the various dimensions of a word. And in the blog, I sort of describe this as, you can think of like, well, one of those numbers might be for manliness, and one might be for royalty, and one might be for some other property. And of course, it's not really like that, but that's kind of the idea, that each of the dimensions has come to represent sort of some element of the world in which these words are used.
Indeed. So king, for example, would score highly on the manliness and the royalty dimensions. I'd like to give a few high-level examples before we dive into the technical elements of this, just to motivate why this is such an interesting concept. So one example you give in your post is the analogy application. So word vectors can be used to answer analogy questions. For example, man is to woman as uncle is to X. If you've got your set of word vectors developed, you can derive that X is aunt. Man is to woman as uncle is to aunt. Explain how word vectors could be used to derive the answer to that analogy.
Yeah, this is I think where it starts to get really, really interesting. So you can imagine you've got these vectors and you've got hundreds of dimensions, and you do something called PCA, or principal component analysis, just to boil them down to the most significant few dimensions that are capturing most of the variability. Imagine it's even 2 dimensions, and you can plot these as then points in a 2D space or a 3D space, whatever you want to use. And so these now become sort of vectors in the sense that you thought about them in school, where you're drawing lines on the axes, etc. And so we can start to do basic vector arithmetic. So you can take, an example, the vector for man, and you can look at, well, what do I have to do if I'm at the point in space which is man to get to the point in space which is woman? And maybe you go, 2 to the right and up 3 cells or something like that. So you've got a 2-3 sort of translation to get from the point, or the vector space where you've got man, to the point which is woman. Now start yourself at the point which is uncle and apply exactly that same delta, that same movement. Where do you end up? And it turns out you end up in the space at a point that's very, very close to aunt. And so by doing these kind of very, very simple vector operations, you're somehow exposing some of the meaning that's been captured by these vectors. And it's very surprising, just exactly what you can do. And the analogy one is a great example, but there are many others. For example, taking a city and relating it to a country, then you can take some other city and out will pop, the country that it's in, etc.
Yes, or finding the relationship between a word and its plurals. For example, king to kings or queen to queens. You can also do, I guess, king minus man equals queen. And I think all of these, you're essentially describing the same kinds of simple operations. Just
Exactly.
Is it all just like these kind of addition and subtraction, or are there some more complex operations you can start to do?
They're all pretty much these sort of simple movements in the vector space. And you described the absolute classic example, which we should go through because listeners will come across it. If you take the vector for king and you subtract man, so in our abstract space maybe we're left with some essence of royalty, and you add the vector for woman, you end up surprisingly at the vector for queen, which is a classic example. And so it really is these very simple. You can add in more dimensions to get more sophisticated, but most of the examples seem to use just a couple of dimensions, and it works really very, very well indeed.
Okay, Word vector analysis is, as you mentioned, this type of principal component analysis. Could you give a little more light on what that word, that acronym means, that principal component analysis? What are some other areas of computer science where these vector operations, PCA, come into play?
Okay, yeah. So PCA is kind of like it's a black box algorithm you could apply in many cases, but the essence of the idea is that you've got a whole range of variables, in this case the dimensions of our vector, etc., and you want to find the smallest possible set of things that can explain the variation you see in that set of variables. And so, well, they might be latent factors. It might not be that just some of the variables are most important. They could be latent, or in other words, hidden causes behind them. And so what PCA does, and behind the scenes, it's all matrix operations and eigenvectors and all that fun stuff that you might have learned in a linear algebra course. But what it does is it tries to find, in a ranked order, first off, the dimension that explains the most variability you possibly can, given only one single dimension. And then the next thing it finds will explain the next largest chunk of variability, and so on down. And so you end up with a ranked set of factors that can explain as much of the variability of your data set as you can, given those. And so it's commonly used to say, look, I've got this massive set of factors. I need to boil it down to something simpler that I can work with, that I can understand, that I can plot. And you might use something like PCA to do that. And that's exactly what we see going on here with these word vectors, to do these little sort of analysis and vector operations.
You have a software project that you want to build. Everybody does. I love building products, but I know more about how software fits together than how to actually write the code itself. I don't spend a lot of time writing code, but I do like to build software. That's why I use TopTal. TopTal is the best place to find reasonably priced, extremely talented software engineers to build your projects from scratch. You can get a pair of Apple AirPods when you use toptal.com/sedaily to work with an engineer for at least 20 hours. And I recommend it. I think it's a great way to build your projects if you don't have time to build them yourself. There's a misconception that engineers have to build all of their own projects just because they're capable of doing that. It's not true. TopTal has only the top 3% of developers. They turn away 97% of the developers that apply to work on the TopTal platform, and that's how you get a matching process that's unlike anything else I have seen in the freelancer marketplace. And I've tried a lot of different freelancing platforms. TopTal has such high-quality engineers, and they listen through the design specifications that you have. They handpick the perfect developer for your project, and this has saved me countless hours in my development process. There's really nothing that compares to TopTal that I have seen. So you can get a free pair of Apple AirPods when you try TopTal at toptal.com/sedaily. Find an engineer that's going to help you build your side project and get your MVP off the ground. As long as you do at least 20 hours, you get those free Apple AirPods. And if you've already got a company that you're working on, you can also use TopTal to scale your team and get everything done faster and raise the bar for your engineering, or get through that blocker that's preventing your company from getting to the next level. So check out toptal.com/sedaily and find an engineer who will help your project succeed. Yeah, when I was in college, I took a course on information retrieval, and that was my first exposure to this topic of vectorizing objects and doing analysis on the sets of vectors. And once you understand a little bit of this area, it really does open your mind. So I encourage anybody who's listening to this and they don't know anything about principal component analysis or about vectorizing objects and doing comparisons between them, I think it really answers a lot of the questions in computer science that might otherwise seem completely magical, like things like search, for example.
Yeah, it's absolutely amazing how many places these vectorized representations pop up and the things that they're used for.
Right. Okay, well, so let's get into the training of a Word2Vec corpus, I guess, or set of words, set of vectors. So you're going to end up with these set of vectors. You're going to have things like king, queen, man, woman, depending on whatever words are in your corpus. Maybe we could talk about the size of the corpus later on, things like that. But we need to get to this place where we've got vectors representing every word in our corpus, and then each of these vectors is going to have some number of dimensions. And like you said, these dimensions you can think of them as representing things like manliness, like how manly is the word man? Well, it's pretty manly, so that cell in the vector is going to have a high dimensionality, and maybe the word natural might have a slightly lower dimensionality, but it's still, a man is still natural, I guess. How do these dimensions get selected, the dimensions for each of these word vectors that all of the words in the corpus will end up getting assigned?
Okay, great question. You sort of at a high level, the answer is quite deep than what you think about it, because really the answer is that the meaning of a word can be very, very much derived by the context in which it gets used. And so if you go back to the original Mikolov papers, he talks about sort of two different ways that you can use sort of machine learning to train or to learn these vectors. And they're really kind of flips of each other. And the simplest one to understand is called the continuous bag of words approach. And what we do here is that you take a sentence and you're going to try and we want to learn the word vector for some focus word, let's say in the middle of that sentence. And so we'll take that focus word and we'll look at the words either side of it. Say we're going to take 2 words either side, or we're going to take 4 words either side, whatever we want to do. And that collection or bag of words that are either side of our focus word, we'll call them the context words, becomes the input to our network. And what we want it to predict, or what we want it to output, is the focus word or the central word that we're hiding from it. And so we want it to learn that when I see this set of context words, I should predict with high confidence the word that I've hidden that was in the middle of the sentence. And we repeat this over the whole corpus, and eventually from this context we end up with these trained vectors that have all the properties that we've just been describing. Now there's a related method which kind of does that back to front, which actually turns out to work slightly better, though it's a little bit less intuitive. And what you do is you start with the focus word, the word in the middle of the sentence. And this method is called skipgram, by the way, if I didn't say that. And instead you're asking it to predict what are the words that surround it in the sentence. So you start with one word, but you're going to predict, say, 4 words, the 2 words to the left and the 2 words to the right. And you run it round that way, and you train it such that it minimizes the sum of the predicted error across all of those words. And you do this over the whole corpus. And once again, you end up with, from the context, this meaning encapsulated in the vector. And it does kind of make sense that when you step back and think about it, there's a lot of meaning in the context in which we use words. And it very, very much does sort of give you some hints as to how they might be related. So, those are the 2 primary methods. There are derivatives we can come on to, but that's the core of it.
Certainly. So I think an example might help. So let's take the sentence, our cow ate green grass. So if you were doing the continuous bag of words, so there's the continuous bag of words, and then, the other one is...
skipgram.
Skipgram, right. So continuous bag of words is, you could, let's say, if you were just looking at 3 words in each contextual set, you could say, our cow ate for the first 3 words, and if cow is the context word, then you would have, R and ate would be 2 words that would get plugged into the context of cow, and then you could slide the bag of words window, and then you would calculate the dimensionality, and you would have some information based off of that set of bag of words, and then you could slide the window over one, and if the sentence is our cow ate green grass, then it would be cow ate green, and then you would get ate as the context word in the middle, and you could derive information relating to ate as related to cow and green. Am I explaining that correctly?
Yeah, that's exactly right. Yeah, you slide through the sentence, and as you say, you take the triple of cow ate green, so ate becomes the focus word, And in the continuous bag of words, therefore, we give it cow and green, and we're asking the model to predict the word 8. And in the skipgram world, we give it the word 8, and we're asking it to predict cow and green.
Mm-hmm. Okay. And then, right. Okay, got it. So could you give a little bit of a deeper explanation for the training process, like how these vectors get manipulated and how they eventually turn into these weighted, where they, where there's an actual, a deeper, rather than just the contextual vector, how we get from the contextual vector to the weighted vector where each word has a deeper set of meanings?
That's right. So if you could imagine, inside of the neural network, we've got a set of weights that are controlling sort of what happens when I feed in the original words. And the original words, by the way, when they come in, they're just one hot encoded. So there's like just the one entry is set to one, as it were. There's a couple of weight vectors that we're going to use as we go through training the neural network. And so what happens is we pump those in, we run the calculations, we get the answer out. And then we see, well, how far is that answer from what we wanted? Are we predicting correctly the two words, in this case, the two output words that we expected to find in the context, or have we got some error? And if we've got some error, then we go through a process which in the machine learning world is called backpropagation, which figures out how can I make small tweaks to all the weights that were in this network so that next time I see that, I'm going to get closer to the desired result. And so you do this backpropagation process that tweaks the weights inside the network. And you do this again and again and again and again and again. I mean, we're talking about sort of maybe billions of words in some of the corpuses that Google have trained, or billions of tokens is sort of a vocabulary of maybe sort of 1 million words or so. So you've got to do this a lot before this starts to refine and really capture the meanings. But this is the process. And so it's actually quite amazing how a very, very simple thing, in essence, just doing this tiny step again and again and again and again. But if you do it enough, it builds up and you're left with the meaning at the end.
Mm-hmm. And if I remember how neural networks work correctly, you have this set of weights that gets initialized randomly, and
exactly.
and the weights, the space in which you can explore different sets of weights forms a gradient, and you're exploring that gradient over time and trying to get closer and closer to a set of weights that produces word vector outputs that make sense when used up against some training data you have, some labeled training data. So you have some sort of labeled training data that you can actually test the output of these word vector generating neural networks against. Is that right? Am I describing that right?
Absolutely, yeah. You start off with random weights, and obviously, in this case, we've got plenty of available training data to us. It's essentially any corpus of text you want to learn from. I mean, given that it's going to use the words in the same context within that corpus, and so for this particular approach, we don't need to have lots and lots of what's called labeled examples for supervised training, etc. We just need lots of sentences in which words are used, and we have plenty of those, and so we feed them all into the machine. And so this backpropagation method, which is indeed looking at sort of gradients to see which way do I need to move to minimize the error, gradually converges to a set of weights that get as close as possible to making the right predictions over time. And that set of weights comes to embody what we ultimately call the word vector.
How do you measure the error in each iteration there?
So normally you're looking at what was it that I predicted, and if you think about sort of the predictions, so what we're going to do is we're going to output a prediction of, let's say we're predicting the focus word. Let's keep it simple. Let's say we're doing, therefore, the continuous bag of words example, because we're going to predict a single word. And, sort of the perfect answer for this particular sentence, say we're trying to predict the word cow, would be a vector with, one dimension for every word in our vocabulary, and it's set to 1 at the moment where cow is, and it's set to 0 everywhere else. What we're actually going to predict is sort of we're going to have values all the way through my array, and they're going to arrange between 0 and 1. And what we want is the nice peak around the word cow, but they're going to be little sort of smatterings of stuff elsewhere. And there's something called softmax, which will normalize everything through to between 0 and 1. And we're just looking for, does it have a nice strong peak around the point where cow is? And so that's what we're really trying to do.
Okay, I see. So, yeah. Okay, that makes sense. And then, okay, so once you've got these, you can do these kind of analogies and these things that we've been talking about. So you mentioned the skipgram approach and the continuous bag of words approach. Are there any other approaches to the training process that you've looked at?
There are a couple more that are fairly well known, and then there's some tweaks that make skipgram kind of efficient to train because it can be quite slow, sort of doing it in the default way. And so we should definitely talk about GLOVE, which is an approach called Global Vectors for Word Representation. And it's a very similar idea, which is that the meaning of words is captured in the context in which they're used. And what GLOVE really says is, instead of just looking at it sentence by sentence, we could look at the whole corpus in one go, and we could look at what's called the co-occurrence matrix. So this is whereby does the word ice often appear in combination with the word solid, for example? How often does that happen? Does the word ice appear in combination with the word gas? How often does that happen? And so we can look at the probability or the likelihood that all these pairs of words co-occur within the corpus. And actually what happens in GLOVE is that you train these vectors to so that they're predicting, if you take their dot product, they predict this likelihood that the two words co-occur. So sort of behind the scenes, it's really a very similar basis. It's looking at the context in which words appear together. It uses slightly more global information. As the authors of that paper say, really ultimately, this is all just statistical methods looking at kind of how often words occur and the context that they occur in. And so they claim some superiority in the fact that they're looking at this on a global basis. But it takes a lot of space to build up this co-occurrence matrix and train it. But they get very good results with the word vectors that come out of this. And then there's an approach called fast text, which you might also see mentioned. It's out on Facebook, if I recall correctly. And that's actually very similar to the core mechanisms we've been discussing with skipgrams and continuous bag of words, etc. Only what they do is, instead of taking each word exactly as it's found, they'll also take all the sort of character prefixes. And so I think if I remember, like, one example is take the word sunny, they'll also create vectors for sun and for SUNN and then for the full word sunny. So they've got all the prefixes, from 1 to n characters, and they claim some advantages for that with sort of less frequently used words, or with being able to cope with words that are what we call out of vocabulary. So there's the things that you've never seen before, but maybe by doing this truncation, you get something that actually can cope with it. So you've got the fast text method, and then you've got extensions which take the word vector idea and give you vectors for sentences and for paragraphs and for documents, and ultimately for other types of content as well. And maybe if it's interested in it, we can get into how some of those work, but they're very interesting too.
Yeah, actually, I would love to do that because we talked about the example of doing basic arithmetic between these vectors and saying queen plus man equals king, and that's a nice little toy example, but Google and Facebook are putting tons of resources into building and using word vector sets, so there must be some bigger scale application to these. Why don't you talk about how these can actually be used, or I think you're alluding to some higher level applications there.
Yeah, absolutely. Yeah, that's a great lead-in. So we've seen how we can have word vectors that somehow represent the meaning of a word, and we can take the same idea and we can say, well, what about representing, for example, the meaning of a paragraph? Does a paragraph have a meaning? What's that all about? And maybe here we'll say if we could have a vector that then captures the topic the paragraph is discussing, which sort of starts to see, I think, why this may become useful. Now, how they do that, and it's a paper that is called How We Get Sentences and Documents. So just find the title. Distributed Representations of Sentences and Documents is the paper title. And what they do is that, as well as having a vector you're going to train for every individual word, they also have one vector, just one additional vector that represents the paragraph, and they make that an additional input. And you can imagine that now we need to get some context words, and we're just going to take a random sampling of words within the paragraph for our training, alongside the paragraph vector. And it turns out surprisingly well that this makes vectors that somehow come to capture the topic or the essence of what the paragraph is about. And so then you can see some examples that sort of have been used for this. So one I think that's in the paper is you could think about movie reviews. Are these somehow about the same movie? And maybe there's other ways we can tell that. Or another thing they did, getting closer to a commercial use case, they looked at collections of search results for the same terms. And they computed the vectors for the documents that have come back. And they found that, yes, indeed, you can see that documents from similar search terms end up with similar vectors, and documents from different search terms have different vectors. And so now we can start to do things like, well, let's take all the named entities that we can find across the web. Let's make vectors for those. Let's do things like finding common phrases like the New York Times is not a single word, but we can see that occurs a lot in corpuses, and so we can make a vector for the New York Times. And now, I could start to use that to do smarter search. So if you ask me for sort of things related to a term, as well as doing the standard sort of TF, IDF and other sort of search things that we've done for years, we could say, well, what things are similar to this in the vector space, for example, and we could start to use that to return results. And indeed there was, I'm not sure how much sort of Google have talked about this publicly, but I think they've gone some reasonable way, but there was a 2016 patent application from Google, for example, that talked about using these kind of context vectors to enhance the search that they're doing. So you can see that this is getting quite deep into the core businesses.
CloudFlare runs 10% of the internet, boosting the performance and security of millions of websites. Many of you probably already use CloudFlare on your sites, but we're not talking about using CloudFlare today. We're talking about building on top of it. If you're a developer, you can build apps which can be installed by the millions of sites which rely on CloudFlare. You can even sell your apps. They can make you money every month. Your users can log in or register to your service inside your app. They can get a real-time preview of your tool live on their site, and they can start paying you monthly, all from within CloudFlare apps. They can go from never having heard of you or your service to having it installed on their site and paying you in seconds. Visit cloudflare.com/sedaily to watch how you can build and deploy an app in less than 3 minutes. That's cloudflare.com/sedaily. Thank you to Cloudflare for being a new sponsor of Software Engineering Daily. Well, that's no surprise. I mean, if you think about it relative to PageRank, PageRank is, okay, we've got these links throughout the internet. Maybe let's see if these links actually are contextual information for how useful a certain page is. Oh, it's quite useful for that. And this is just taking it to a lower level and saying, well, let's look at the words surrounding this word. How useful is that to describing what this word does? Oh, it's quite useful. It's almost like PageRank for a word-wise analysis.
Right, exactly. And so another example that Facebook have talked about, they have the Facebook AI similarity search. They take a similar idea and they build a vector that somehow represents what a video is all about, for example. And now you can do similarity search on videos based on these vectors, which of course is very, very fast and simple to do. Why would they want to do this? Because it's content recommendation, of course. And what should they push you? What should they show you? How do they engage you? So you can, these vectors pop up in all sorts of interesting places.
Now, this sounds like something that to a machine learning researcher, this idea is probably kind of intuitive. Why are we starting to hear more about this now? Was there something that changed recently, like processor speed or storage or compute cost, or the frameworks got more easy to use? Like, it seems like this should have been done like 10 years ago.
Yeah, I guess it's a combination of all of those features. Sort of even when we had the original sort of Word2Vec paper, which introduced this sort of word vector notion that we're talking about. There had been distributed representations of words before, but one of the things that Mikolov did in that paper is they showed a couple of techniques for learning this very efficiently. So that's one. Sort of doing this at scale, as we touched on, you need a very large corpus. You're going to crunch a lot of words. It takes a lot of training time. We've got the platforms that can do that. We've got the GPU accelerations. We've got the TPUs, etc., inside of Google to make that kind of thing efficient. We've also got some algorithmic learning. There's some techniques like there's one called hierarchical softmax, and they use something called negative sampling to basically just make the training go faster. Taking in some understanding about the domain. So that there's a little bit of sort of practical side of it. And then I think there's something we touched on, right at the beginning of the show, which is, it really put the idea out there that it's obvious once you've heard it that these numbers can capture the meaning, but the extent to which they do is really quite surprising and very pleasing. And so, as we said, it's sort of spread from words to, hey, you can do this to sentences and paragraphs, you can do it for documents, you can do it for video, you can do it for image. There's some fun things around images, maybe we can get to talk about those as well that have been done. And so I think it's kind of like the idea has gradually spread through the consciousness that this can be done. We've seen some high-profile successes with some of the approach, sort of improving results. We're getting state-of-the-art on many benchmarks, starting to be commercially used. And so, it's become top of mind as a way that you could do it. And I think all those forces come together.
Okay, what's the image stuff you're talking about?
Okay, so the image stuff, I found this sort of particularly pleasing when I first encountered it. And so I'm going to have to explain this in sort of two levels. So we start off with this idea called generative adversarial networks, which came from Goodfellow in, I think it was 2014. And this is where we want to make a network that's going to conjure up realistic looking images for us. Sort of just make pretend images that look realistic is the goal. And that's not an easy task, and it's a particularly fun way of doing that. Sort of pits two networks against each other. And so you've got, which is where the adversarial part of the name comes from. So you've got what's called a generating network, which is trying to create images. And you've got a discriminative network, which is trying to say, is this a real image? Like, is it a photo of the thing that I'm interested in, for example? Or is it one that's made by the generator? And you train these things sort of squaring off against each other until the discriminator can't really tell the difference anymore. And at that point, you assume that you've made a generator that's able to produce realistic looking images, at least as far as this discriminator can't tell. And that works really surprisingly well. You take that idea and make your generative networks be based on something called CNNs, which are convolutional neural networks, which have been sort of all the rage in the image world with deep networks. So make a generative pairing using CNNs and let that run for a while. And then let's take a step back and you say, well, hold on a minute. If this deep CNN is able to generate images that look realistic, somewhere in the middle of that network must be something that has learned some understanding of the features or components of realistic images. What is that, and can we find it? And so what the researchers did is that they looked inside, and in the CNN you've got these sort of features that you use for convolution, sometimes called kernels, and they took those learned feature sets. They said, what if we made these as the vectors? Let's look at what they represent. And then they started to do similar kind of vector arithmetic, and it really helps to see the pictures of this. But for example, if you take, I think in one of the examples, if you take 3 pictures of women smiling and you subtract pictures of women with a neutral expression, and then you add the vectors for men with neutral expressions, what you end up with is pictures, remember these are all generated pictures, so that they're artificial, that look like men smiling. And you can do a similar thing where you add and remove glasses, etc. And so
wow.
What they kind of showed was, it's kind of like, wow, this is really amazing, with, again, like the words, with no human sort of explanation, that this network from this generative form, unsupervised training, was able to figure out that there's some kind of meaning in these features in the images, and it was able to learn an encoding for some of that meaning that when you manipulate it, makes sense to us when we look at the generated images, which is really quite mind-blowing.
Yeah, and similar applications with the video stuff that people have, I'm sure, all seen if they're listening to the show, the video of the fake Obama talking or fake Trump talking, or you can make these fake videos of people talking. Similar processes. Where do these kinds of generative networks fall over? Like, or more broadly, what are the bottlenecks here? Like, what's keeping us from, for example, easily generating really convincing fake news stories or really convincing fake videos? I mean, we've seen the stuff of Obama talking, but that seems to only be in the lab. I guess it's either contrived somehow, or maybe there's you still need like a supercomputer to train it. Do you have an idea for what the bottlenecks are here?
Yeah, it's tricky. I mean, sort of, I guess, certainly when you're trying to do something for a human, it's well known we have kind of the uncanny valley where you get sort of very nearly but not quite, and we seem quite tuned in to picking up on that as humans and finding that disconcerting. But I guess I recently looked at a paper that touches on this topic a little bit, which is to give some examples. It was the question of sort of style transfer in images. You may have seen last year there was the app called Prisma, where you take sort of an artistic style like a Van Gogh painting or something, and you give it one of your photographs, and it renders your photograph in that style. That's called neural style transfer, and that's another thing that sort of caught many people's imaginations. It has been widely sort of used and many derivatives, etc. And so for the longest time, what that process would do would generate sort of output images that looked like works of art, i.e. paintings, but didn't look like photographs, even if the input was a photograph. And so the interesting question is, well, sort of, why doesn't it look like a photograph? And what could I do to get sort of photorealistic output, which is sort of nudging, I think, towards the question you're opening with. And so a group of researchers looked at this, and in that particular case, they were able to crack the nut. And so they produced a system in which you can have a reference photograph, say, of a nighttime scene or whatever it is, and another photograph, say it's a skyline in the daytime, and you say transfer the nighttime reference style on top of this daytime, and you get a picture of the city at night, and it looks like a photograph. And so in this case, what they had to do was a couple of things. One was, in the training, they had to be very in the generation, they had to be very careful to say you can only do transforms that don't move edges and don't distort certain features in the image. And previously, these generative networks didn't have that constraint. They put this constraint in so that sort of like windows in a grid, for example, won't all sort of start moving and wobbling. They'll stay as they are. And then the second thing that they had to add, which again is quite interesting and it sort of touches a little bit on what we're talking about, they had to go back and do what we call segmentation, which is to look at the image and try and figure out to some reasonable level what the different parts of the image represents. This is a building, this is sky, this is a tree, whatever it is. And then when they're doing the style transfer, they map from like segments to like segments. So you don't want, for example, as happened in the previous generation, you don't want a pattern in the sky to suddenly end up on the building or vice versa. And by doing this sort of segment-based mapping, they're able to constrain it. Those two things combined gave us much, much, much better photorealism. You look at some of the output from this, and it looks pretty darn good. So that's an example where we were getting close, we were getting close, and a couple of extra constraints, a little bit of domain knowledge sort of seeped in there, and it got us over the line. In a number of sort of areas, we've started to see now that sort of these learned approaches are starting to meet and exceed sort of human levels of capability. So I think it's coming, but there's still for every given domain, there's still some tremendously hard problems. I wish I had a sort of the universal answer. If I knew what that thing was, I'd probably be working on it if I was skilled enough. But I'm amazed at the progress the field seems to make. Almost quarterly, let alone yearly.
So do you think it's more of a challenge in the implementation of the strategy and just architecting the strategy for your neural net, rather than it's not like some processor speed thing, it's not like some compute cost thing, it's like how are we supposed to phrase this problem to the machine? That seems to be more the issue. Is that correct?
Yeah, I mean, there's always kind of the brute force element to sort of deep learning. Like more is better, more data, more machines, more training. Throw everything at it and it works better. But for the really interesting breakthroughs, I think it is going to be slightly smarter models, approaches, sort of ways of doing things. And there's many examples of that sort of coming along. For example, the last few years we've had this introduction of memory, so that we give these things a memory in a form of what's called an attention mechanism. So it's kind of they can store things in memory and they can decide what to focus on and use it later, and that's given us a leap forward. We moved from human designed features to machine learned features, and that gave us another leap forward. So we're always sort of pushing at it, but I'd like to think the answer is more than just brute force. It would be somewhat disappointing if that was all we needed.
Okay, so getting back to word vectors, and then we'll wrap up with some other stuff. But the word vectors, so I'd love to get a picture for the open source landscape. So if I am correct, I think Google has released a set of word vectors. So they've trained a giant set of word vectors. And so there's those. And then there's also open source projects for building your own word vectors from whatever corpus you want. Is that correct? Or can you give me a landscape for the open source projects of word vectors?
Yeah, that's right. So I'm certainly not sure I know all of them, but definitely you're right. There have been some sort of released pre-trained word vectors. There's the corpuses of them that you can go and grab and just use as inputs then to any other task, any NLP related task, for example, that you want some understanding of words. They've shown to give you a good leg up and get you going quickly. So Google, I think, trained a set on a corpus. I think it was Google News corpus with about 5-6 billion kind of word tokens in the corpus and a dictionary of about 1 million words. And they trained that, and I think they've made that available. And I think they also made available a named entity one. I've got a half recollection that there's a set of pre-trained word vectors also available from Stanford, and that out of their NLP group. I could be wrong about that, but I think they have done that. That would be related to the GLOVE project, which came from Stanford. And then you've got their open source implementations of Word2Vec itself. Facebook have their fast text library. I think there's some Microsoft cognitive intelligence stuff that they've done, and I believe there's some pre-trained vectors available as part of that as well. So I haven't fully kept up to speed on that, but definitely there's no need to go and implement this from scratch anymore. You can get both the code for training the vectors and also pre-trained vectors themselves, sort of widely available these days.
Yeah. So I was listening to an episode of the Women in Tech show, which is a podcast that I listen to sometimes, and they were talking about bias in these types of machine learning models. Is there any risk of bias of the corpus being biased in a certain direction and it leading to problematic word vectors that don't actually represent reality?
That's a fascinating question. Yes, so I guess to be clear here, we're talking about sort of bias as in discrimination, not bias and variance, which is another kind of machine learning topic. So I was referring to both.
Okay,
great. So, it's absolutely the case that what's in your corpus is going to reflect, what you learn. We used to have the old phrase kind of garbage in, garbage out, when we talked about sort of IT systems and sort of, there's a related one, I think, for the modern era, bias in, bias out. Definitely the machine's going to learn whatever is in there. You might find if you took those word vectors and did some arithmetic, you might find some relationships in there that you'd really rather weren't in there. That's entirely possible. I've not looked or seen anybody doing that study, but it actually wouldn't surprise me unless care had been taken to do it. And there's a bunch of research actually starting to look at how can we create learned models, not just word vectors, but all sorts of things that are free from bias, that are free from discrimination. And that's actually not an easy problem. Likewise, they can sometimes leak a lot of information that you might want to have kept private about the data they were trained on. That's another related problem. Sort of the features, the warts and all of what you put in, showing through and still being represented in the trained models that you get out.
All right. Well, I want to talk a little bit about some aspects of the intersection of venture capital and software engineering, because you're a venture capitalist and you worked for a long time in technology. You still work in technology. So just shifting pretty abruptly, I've got some questions. One question I've been thinking about a lot lately, and I talking to some people about this, is whether the cyclicality in the investment cycle of technology companies has been reduced or perhaps eliminated. And the reason I bring that up is because AWS, or more recently other cloud providers, they've really eliminated the upfront capital costs to building technology companies for a lot of people. And so it almost seems like, since companies can get to a place where they have a pretty provable business model, it seems like that erases a lot of the cyclicality in the investment cycle, except for obviously the sensitivity of LPs to the the natural business cycle and the ups and downs of the stock market. But I don't know, to what degree do you agree with that statement, that AWS or cloud computing has eroded some of the cyclicality?
Well, certainly, it's a wonderful time to be starting a business. I think it sort of continues to be true, but it's in that sense never been a better time. The the resources that are available to you with minimal outlay to get you started. Even the programs from all the various cloud vendors will give you loads of free credits and all sorts of stuff, as a young startup, if you apply into their programs, etc. Couple that with the endless sort of services that are out there to support the business. You can get almost anything as a service. And so you can incredibly quickly pull together pretty comprehensive solutions in which you've had to focus, much more just on the part that's unique to you. And you're able to pull together kind of pre-built components, services, relying on the cloud platforms, etc., to do the rest of it. And so you're right, you can sort of very quickly and with much less capital outlay, much of this kind of on operating expenditure on kind of monthly, you can get going really fast and you can build the initial version. Still the case, it's still incredibly hard to build a really, really good business, and to find the magic, the product that works in the market and to get it all going, the right way of selling it, the right way of packaging it, the right collection of features, the right market niche, etc. So it's not like the hard bit of doing the company is any easier, but a lot of the surrounding stuff is done. And maybe you would think that this sort of operating expense model would smooth out the need for capital and sort of everything would come through sort of at a point where it was well understood and come for funding, and it would be it's a very scientific process, but it's still, sort of, at least I find it's tremendously difficult when you meet all the companies in the varying stages of very diverse sort of problems to try and judge which ones are going to be the winners, which ones, or at least which ones have a chance of being a winner, which is really as much as you can really do. And you do still see, I think, cycles in, let's say at least in valuations. And so if you go back sort of maybe 18 months, there was sort of relatively high valuations, lots of competition, particularly in the Valley, sort of around funding companies. And so sort of if you've got there the obvious, let's say the obvious, but the very strong proposition, great founders, really good looking product, and sort of, everybody's sort of raving about it. That everybody wants to fund it, everyone wants to be on in that investment. That creates kind of high valuations, which at some point you have to step away and say, well, actually, at that valuation, it's not a good investment. And so you still get those kind of cycles going through. We've been through one, valuations went very high, they're coming back down to be a little bit more sensible now. And so I don't think the full cyclicality is ever going to go away. But in terms of, what you need to get started, it's a terrific time.
Interesting. Okay, last question. From your point of view as an investor and a technologist, what's something at the intersection of distributed computing and machine learning that you think is underappreciated and perhaps would make for an interesting investment opportunity?
Oh, that's a great question. Two things I'm definitely sort of quite keen on and have followed. I guess if I think about that, one of the things that in many ways is still far too hard is understanding what the hell is going on, basically inside a distributed system, and sort of the bug that only occurs kind of like once every 24 hours in production, and you never quite manage to catch it. What is that? What's going on? With the combination of all the increasing, let's call them observability technologies that are starting to capture the traces and the other information, and some smarts that researchers have been looking at to sort of probe on what's going on inside the systems, plus the ability to learn, analyze, from that. Maybe there are some smart things to do to help us sort of troubleshoot and operate these things better. Maybe even to build them a little bit better in the first place. Now, and let me sort of finish maybe on this one thing that I'm not sure is a great investment idea, but I love it as a technology idea. You've just reminded me of it.
Yeah.
Which is some research I saw recently that takes the idea of word vectors and says, well, what if they were kind of inside the database? And so the idea is that you take a relation, let each row in the relation be a bit like a sentence, and do a similar kind of training process we've been through. Maybe there are real words, maybe they're just sort of tokens, and we'll learn a vector for each token that appears in every column of that database. And if we did that, maybe we could answer a different set of queries to what you can do in a relational database today. So sort of, I think they call them cognitive intelligence queries. I'm sort of trying to remember as we speak. And so what would be an example? You could say, find me all the people that purchased a basket of items similar to this. Classic use case. Yeah. There are many ways of doing that, but you could do that kind of thing based on the vectors that have been learned inside the database. And that's something that actually they show how to express it in sort of like a SQL extension. It's really quite interesting. Or you could do, say, if you had an external corpus and you'd learnt a relationship, I think one of their examples is between sort of certain foodstuffs and allergens, you could ask a query in the database based on this and say, well, tell me all the things that people have purchased that they might be allergic to. And so you can start to ask what they call kind of like semantic queries that are nowhere in these syntactic kind of foreign key relationships, etc., between the data, but they're on another level. And so that kind of really interesting, like, here's a totally different way of looking at it, where you can do something that the more you stare at it, the more you start to get it. Is quite interesting and haven't been seen before. I'm a sucker for anything like that. I love it.
Well, it's pretty low hanging fruit too.
Certainly when you read the paper, you can see very clearly, sort of, this is the mechanism they went through, this is how they did it. You can begin to understand the implementation for sure.
Okay. Well, Adrian, thank you so much for coming on Software Engineering Daily. It's been great talking to you.
Oh, my pleasure. Thank you for having me.
We're trying out something new with the Software Engineering Daily question of the week. This week we want to know, what is the best continuous delivery or continuous integration tool, open source tool or platform, some software as a service that you use? We want to know what is the best continuous delivery tool and why you're using it. Send me an email, jeff@softwareengineeringdaily.com. We're going to evaluate the answers, and we will select a random person who emails us and award that person with a free Software Engineering Daily hoodie sweatshirt that we will send you. And then we will compile those answers. We'll get you a write-up in a month or so with the feedback for what is the best tool. So send me an email, jeff@softwareengineeringdaily.com. We would love to hear what you think about continuous integration and continuous delivery tools.
Wow!